Hi there, welcome back. I'd like to go through two more examples of first-order differential equations that can be used to model real-world situations. So the first one is a temperature model. So that involves Newton's law of cooling, which gives the behavior of how the temperature of an object changes subject to the ambient temperature. So what we're talking about here is that if you leave some liquid hanging out in the middle of, you leave some coffee out, and you decided that you just leaving it, it's really hot, but then it's cooling down over time. And the question would be, well, how would that temperature of the coffee change over time? And so Newton's law of cooling says that the change, d capital T, d little t, and I know it's a little confusing to have t's all over the place, but that's what we've got. dt dt is equal to some negative constant, so a negative positive constant, of T minus the ambient temperature, T naught. So when the temperature is too high, when the temperature of the coffee is higher than the room temperature, then we expect that the temperature to go down. But if on the other hand you have some cold iced tea and it's in a warm room, well then the T minus T naught is a negative number, so then this whole quantity is a positive number, which tells you that the temperature is going to increase over time. In chapters 15 and 16 of the book, there's the concept of and let me say one last thing, which is this R is dependent on the situation, dependent on the object or the liquid that's cooling or heating. This is object dependent. So in chapters 15 and 16 of the book, they talk about two liquids that are both changing over time. Maybe this is R1 and this is R2 of S minus S naught. And so let's say you have some cream in the refrigerator and some coffee that's out on the counter. When should you add one to the other? Or what happens if the temperature outside changes? How's that going to impact the temperature of your coffee? So that's one model that has to do with figuring out how, and then if you mix them, then they can be interdependent ideas. So that's a model that we can use to simulate the real world. And the last one I want to talk about is this idea of the minimal model for glucose. So your blood sugar level or your glucose level in your body is controlled by the insulin that's provided by the pancreas. So what we might want to know is how much glucose do you have in your blood and how much insulin do you have in the tissue fluid, because that's where the interaction happens between those two levels. So we're going to write down some differential equations, but the differential equations are going to depend on something that you can keep track of. You can keep track of how much insulin you have in your blood. You can keep track of what your equilibrium blood glucose level is, your equilibrium tissue fluid insulin level, and just there's some system variables. We might need to figure those out or model or find the right values for those. But given these quantities and these maybe known quantities or parameters, then what we're goal to do is to create this differential equation system. We want to see how these concentrations are changing over time. Okay, so let's write down these equations. So these first equations are going to look like the coffee cooling setup, where if we're looking for dg dt, how does the glucose change over time? So the rate of glucose, the rate at which glucose is changing is going to try to revert back to its base level. So if we compare the glucose to G of t minus Gb, if we compare the glucose level currently with what the base level is, the glucose wants to get back to that base level. So glucose wants to revert to its base level. All right, but then there's the connection, the interaction between the glucose and the insulin. So x of t, g of t. So this is the interaction between the glucose and the insulin. And so basically, if x or g or both are large, then the glucose is going to go down. So that's the first equation. And now the second equation, dx dt, tells us that so this is K1 up here, here's K3. So this one is telling us that the rate of insulin transfer depends on how close the insulin is in the blood is to its to the equilibrium level. So this is rate of insulin transfer from the blood to the tissue. Due to the blood insulin level. So if your blood insulin is really high, really far away from the blood, from its equilibrium value, it's going to send more insulin into the tissue. And then minus K2 times x of t, so rate of insulin disappearance due to being used or broken down. So these are the two equations that influence how g and x are interrelated and are related to those other quantities. So this is one more differential equation model. You can imagine actually trying to model somebody's glucose level based on some collecting data, or just exploring this direction a little bit further. All right, so that's a bunch of models. Take a look, have see which ones are the most interesting to you. Of course, you can also take the SIR model and develop that further, putting in more states. Explore, see what you can figure out, and we'll talk about it. All right, take care. Bye.